Every single 24 hours, the WhatsApp network processes over 100 billion individual messages. It maintains 99.99% operational uptime, and it guarantees sub-100 millisecond delivery latency for almost every single payload. That infrastructure serves more than 2 billion users across 180 countries. When Facebook acquired the company in 2014, the team responsible for building and maintaining that entire global backend consisted of exactly 50 engineers. To understand exactly how that is physically possible, we have to isolate a 100 millisecond window and trace the exact algorithmic steps a message takes from a sender's device to a receiver's screen. What you will see is that achieving an 18 million to 1 user-to-engineer ratio required the founders to completely abandon the standard enterprise technology stack from day one. Look at this diagram detailing the standard HTTP protocol. In a normal web environment, a phone has to constantly ask the server if new data exists. This request and response cycle creates massive bottlenecking. The server cannot push a message to a phone unprompted. The architectural solution sits on the right. WebSockets. When you open WhatsApp, your phone establishes a permanent bidirectional TCP connection. The pipe stays open, allowing data to flow in either direction instantly. To keep that pipe open without overwhelming the network, the app utilizes a ping-pong heartbeat mechanism. The phone sends a tiny data pulse to the server, and the server pulses back, confirming the session remains active. If 60 seconds pass without a heartbeat returning, often because a user drove into a tunnel or lost cellular service, the server assumes the connection is dead and kills the process to instantly free up compute resources. Relying on this persistent model allows a single WhatsApp server to handle 2 million concurrent connections. Supporting 2 billion total users requires a fleet of just 200 front-end servers. Eliminating the constant overhead of HTTP handshakes at the network edge creates the physical prerequisite for sub-100 millisecond message delivery. Holding the connection is only the first step. You also have to format the data traveling through it. Standard chat protocols use XML, which is notoriously verbose. Parsing heavy XML text burns smartphone battery life and clogs weak cellular connections. WhatsApp engineered a custom binary protocol to solve this, internally named FunXMPP. By stripping out the text-heavy formatting of XML, the FunXMPP binary format reduces the total data payload size by a factor of 5. Your phone encodes your text into this dense FunXMPP block and pushes it through the WebSocket. The moment the server decodes it and assigns a message ID, it triggers a single gray tick on your screen. That same hyper-efficient binary format is also used to carry all present-state metadata across the network. That includes the typing indicators and your last seen timestamps. Shrinking the data payload at the protocol level ensures that the application remains operationally reliable, even on the most degraded 2G cellular networks in the world. Moving that data efficiently is useless if the transit isn't secure. WhatsApp's end-to-end encryption relies on a strict architectural premise. The servers must act exclusively as a blind relay, never holding the keys to the data they transmit. This chart visualizes the initial asymmetric key exchange. When you register a device, it generates 2 keys. A gold public key is sent to a central server database. A red private key locks itself permanently inside the physical hardware of your phone. Using the open-source Signal protocol, your device pulls your recipient's gold public key and uses it to encrypt your message. It becomes an unreadable blob before it ever hits the network. The server routes that blob, but only the recipient's red private key can decipher it. To prevent a single compromised key from exposing a whole chat history, the protocol uses a double ratchet algorithm. A mathematically unique key is derived for every single message sent, securing both past and future data. Modern updates have layered post-quantum key exchange, or PQXDH, over this system, protecting current encrypted blobs from being cracked by future quantum computers. In a group chat with 1,024 members, the server doesn't decrypt and distribute the message. Instead, the sender's device encrypts that single message 1,024 separate times locally before transmitting it. This cryptographic architecture makes privacy a mathematical property of the transit layer. The server is physically incapable of decrypting the data it carries. Handling millions of these encrypted, persistent connections requires an unconventional compute paradigm. The backend is built almost entirely on Erlang and the Beam virtual machine. Erlang was developed by Ericsson in the 1980s for telephone switches, requiring 5 nines of uptime. A standard operating system thread consumes about 1 megabyte of memory. An Erlang process consumes roughly 2 kilobytes. Look at the scale difference. Because Erlang processes are so lightweight, the Beam virtual machine can spin up and manage hundreds of thousands of isolated processes simultaneously on a single server node without crashing. This utilizes the actor model. Instead of threads fighting over locks in a shared memory pool, every WhatsApp user connection gets its own isolated Erlang process. They communicate strictly by passing messages directly to one another. Because the processes are isolated, engineers can execute hot code swapping. They load new backend code while the old code is still running, updating the system without dropping a single active user WebSocket. By completely rejecting the standard OS threading model, the engineering team bypassed the traditional compute limits of server concurrency. To route those millions of messages efficiently, WhatsApp relies on Amnesia, an Erlang-native in-memory distributed database. It acts as a massive routing table, tracking which server currently holds the active WebSocket for which user. The backend operates on a stateless flow. The system is a relay, not a vault. As you see here, messages are only queued in temporary RAM if the intended recipient is currently offline. The precise trigger for data destruction is the second tick. The moment the server receives a delivery acknowledgement from the recipient's device, the message fires, and it is immediately wiped clean from the server's memory. Refusing to store message history eliminates the need for massive database scaling and complex distributed locking. The data layer remains remarkably light. Pushing this architecture to its physical limits required one final, counterintuitive choice at the operating system layer. WhatsApp runs on FreeBSD, not the industry-standard Linux. The core bottleneck of hyperscale messaging isn't CPU power, it is the OS kernel's ability to efficiently notify the application about network events across millions of persistent TCP connections. The engineering team found that FreeBSD's KQ networking stack processed this extreme load with significantly less CPU overhead than Linux's equivalent ePOL system. They aggressively tuned fine-grained kernel parameters within FreeBSD to push the servers past the standard 2 million connection ceiling. True scale requires optimizing the literal OS kernel, moving packets across the network interface card. Operating at this scale means hardware and network failures are continuous. To handle this, Erlang employs a let-it-crash philosophy. Rather than writing thousands of lines of defensive code to catch errors, the system allows failing processes to die and relies on automated clean restarts. This chart shows the supervision tree architecture. Designated supervisor processes do absolutely nothing but monitor worker processes. If a worker node crashes, the supervisor instantly spawns a fresh replacement with a clean state, isolating the failure. WhatsApp scales this exact concept up to the hardware level through islands. The global backend is logically partitioned into isolated, redundant clusters. Within these islands, there is strict primary and secondary replication. A secondary node sits completely passive. If a primary node drops, the secondary takes over instantly, preventing a cascading system failure across the network. The architecture accepts software and hardware failure as a physical inevitability. The engineering focus is entirely on building systems that heal themselves faster than a user can notice an outage. A 50-person engineering team supported a global population by rejecting standard enterprise assumptions. They ignored trends and selected highly specialized tools for a very narrow use case: FreeBSD networking, Erlang concurrency, WebSocket persistence, FunXMMP efficiency, and signal protocol encryption. Every single component in this interlocking stack was chosen because it inherently aligns with one strict goal: moving small amounts of data as fast and reliably as possible. WhatsApp's architecture proves that global scale relies on technical minimalism. Success comes from building lean, predictable systems that prioritize automated recovery over complex feature sets.